So in this video, we're going to talk about piecewise defined functions and then how to find the limits graphically from this. So first we need to talk about what is a piecewise function, and the best way I know how to do that is to introduce the concept through the absolute value function. Now the reason I do this is most students, by the time they get to calculus, they have an idea of what the absolute value function is. This is a function that measures the distance of how far we are from the value 0. Okay, so how far away are we from 0? That's what the absolute value function measures. And so it's actually set up, it's defined as a piecewise function. So those absolute value bars, all right, how are we going to graph it? Well, if I have it set up as a piecewise function, then that means that the x value, okay, this is what it is, it's equal to x whenever x is greater than or equal to 0, okay? So that's the x value whenever it's greater than or equal to 0. So what does that look like? So the function x is a line, okay? And it's solid where we are actually defining it. These are x values that are greater than or equal to 0. Okay, so I have it solid where it's actually defined on the piecewise. It's greater than or equal to 0. It's dotted where it's not defined, meaning we're going to use another piece of a function to define the other part for values that are less than 0. Okay. So let's take care of the x values that are less than 0. What do we actually use? We actually use the function negative x. And so negative x is a line with -1 slope. It's going down. And this is defined. Where is it defined for? For x values that are less than 0. Okay, so it's a solid line here. Okay, and then it's dotted over here. It's the exact opposite of that first piece of the piecewise function. Okay. So that's the idea, the final graph. That's why it looks like a V there, because it comes down and then it goes back up. Okay, that's the idea of the V for absolute value function. All right, so that is the easiest piecewise function that I know of, and how I kind of introduce what a piecewise function is. So let's take another example. And so we're dealing with two lines here, okay? So I have a first line is x plus 1, and then that's what it is. And then the second part is the where it's true, okay? So where do I use the curve x plus 1? I only use it for x values that are greater than or equal to 2. Where do I use the line negative 2x plus 7? I only use it for x values that are greater than 2. So the first part is less than or equal to 2. The second part is greater than 2. Okay? So one value that might be important, if you think about this first one here, it's where we intersected, right? It's where we went from using the red curve to the black curve, or vice versa. So where does that happen? Well, for this first one, it happened at 0, right? For this next one, it happens at 2. So one thing we would like to do, we want to make sure that this is actually a continuous function that'll help us out in a lot of ways. If it's not, it's not, but this helps us with the idea of limit. So what we can do is we can plug in 2 into this first one, and I get 2 plus 1 gets me 3. And if I plug 2 in here, even though technically I can't because it's not greater than or equal to, but still if I plug it in, I have -2 times 2 plus 7, so that's -4, and 7 make 3. So these both give me a 3 value, so I think I'm okay. Okay, so it looks like it's going to meet up on both sides, and I get the limit as x goes to 2 is going to be 3, because as we approach it on this side, values that are less than or equal to, so on the left side we're heading towards 3, and as I approach it on the right side, values that are greater than 2, I'm getting closer and closer to 3. Okay, and so when I graph the first part, the line x plus 1, okay, where is it true? It's true for x values that are less than or equal to 2. So less than or equal to 2 is right here, okay? So this is the 2 mark, right? So that's why it's a solid line there, okay? So it helps that you graph it, right? You graph the whole line and you just put the dot, dot, dots where it goes. So it's like you got this solid dot here because it's less than or equal to, right? So it's got that solid. It's not an open circle. Now, the second part, the red curve, okay, this is a negative 2x plus 7. That's this whole thing here. Well, this is only good for what values? X greater than 2. So x greater than 2, where is that true? That's true here, okay? So that's why that is solid and not dotted. And you see that the final curve ends up being this upside down looking V that's not symmetric like the first absolute value one was. But it still kind of has that same nature. Okay, so it's, you know, it's going up and then it changes direction and going down, just in that sense. Okay, so that's the idea there with the piecewise. The big thing to take away is the first part is the what it is, that's the noun, right? And then the second part is the where it's located, okay? That's the position on the x-axis, which parts is it true for. All right, now let's define, we don't have to just have a piecewise function that only has 2 parts. It can have as many pieces as we want it to have, okay? So let's define f of x to be a piecewise function. And I'm going to graph this, so I'll give you a little bit of time. You can pause the video at any point to do this. So you can start drawing it out. Each one of these little boxes just counts for 1, okay? 1 unit. So like I'm going to graph 1 over x. So that's the rational function. It's undefined at x equal to 0. This is going to be true for x values that are 2 or less. So that's going this way. This is where it's true for, okay? So that's what it looks like, all right? So that's values that are 2 or less. That's what we have there. So that's what I do. I'm not going to put my dot, dot, dots, even though I could. There's no reason to put the dot, dot, dots because it's only valid from negative or from x less than or equal to 2 there, okay? Now the second piece is going to be defined as x plus or minus 4, and that's only going to be on the interval from 2 to 5, okay? So that's only on the interval from 2 to 5. So this is a line from 2 to 5, okay? And so that's what that line looks like. Now, if you need the help, like, you know, if it helps you to put the dot, dot, dot so that you know, look, I knew it was a line with the slope 1 that passed through at negative 4, right? That's what that's telling me. You know, that's great. But then just come back and erase those dot, dot, dots when you're done with it, okay? And notice I have open circles here. Why do I have the open circles here? Because there's no bar underneath here, all right? If I had a bar underneath, then that would mean that was less than equal to, greater than equal to, etc., right? So it's strictly greater than and less than in this interval for that piece of the function. Now the last piece is another rational, and this rational is a little different, okay? It's 1 over x minus 6 quantity squared. And so, excuse me, what's different here? Well, this factor, instead of just being a linear factor like that first one is, it's actually square, meaning a multiplicity 2. And if I have a multiplicity 2, that means that we have a degree that is even, therefore it agrees, okay? So what do I mean by agrees? Well, when I go up on both sides are heading to positive infinity. They agree with each other, okay? So that's what that graph looks like, and it's only for x greater than 5. So x greater than 5 is going that way, okay? So greater than 5 kind of looks like that. And that's the green that makes up that. So what I want to do is I want to find the limit graphically. Okay, and so there are some values that are going to be helpful for us, and we're going to list those out. The first one is that f of -1 equals -1. So if I plug in, go to -1, I plug in, I get out -1. There's no problem with that, okay? How do I know that to be true? Well, okay, where is the second part here, right? So x equal to -1, x equal to -1, where's that going to fall? That's going to fall here. It's the only one that's less than or equal to 2. Okay? So that tells me I go to this purple function right here, and I plug in -1. So that's 1 over -1, which gets you -1. That's the idea of the piecewise. The x value, that's the where, right? The next one is 0. Okay? Which one is 0? Well, 0 is less than 2, so that's still in that first one. If I plug in a 0 here, though, I have 1 divided by 0, which does not exist, so that's why I have does not exist there. The next value is 2. Well, where does 2 go? 2 goes here. It's the only one that's less than or equal to. This one is strictly greater than 2, so 2 is not greater than 2, so it's still the first one. So I have 1 divided by 2. I plug a 2 in for x. I get 1 divided by 2. And so that gets me the half that I have there. Okay. Next, I have f of 5. Now, where does 5 belong? Does it belong right here? No, it's got to be less than 5. So, right there. No, it's got to be greater than 5. So 5 here is actually not defined at all and does not exist. There's just a hole there at the x equal to 5, so it's not defined. Now f of 6. 6 is greater than 5, so it falls in this last one. But if I plug a 6 in here, I have 6 minus 6 is 0. So I can't take 1 divided by 0, right? 1 divided by 0, 0 squared, whatever, is still 0. So that's undefined. It does not exist. F of 7, if I plug a 7 in, I'm going to get this 1 here. So that's just fine to have this here. That's just fine. So let's take limits, and we're going to do it graphically. So whenever I see a -1 here, what do I see? It looks like it's pretty nice around here. Like values around, it looks like we're approaching, like if I use my finger, so, let's say this is my finger. Okay, so I'm going to use my finger here, and as I'm moving, I'm getting really close to -1 on this side. I'm going to have another finger over here. And so as I'm moving up, my other finger runs into the same spot. So it looks like I'm okay. This limit looks like it's going to be -1. And so whenever I do this, I replace f of x with what? I replace it with 1 over x because x is -1. So I'm in that first piece of the piecewise. And when I plug a -1 in, I always plug it in to check to see if it'll work, right? And then I get -1 for my answer. The next one that I want you to get is f of x, and I'm taking the limit as x goes to 0. So how does the function behave around 0, right? Looks pretty crazy. On the right side, it looks like it's going up to infinity. On the left side, it looks like it's going down to -infinity. So looking at this, my function is the purple one, so that's going to be this first one, right? How do I know? X near 0 is going to be values of x that are less than or equal to 2. And so that's 1 over x. If I plug a 0 in, guess what? Everything just falls apart, right? 1 over 0 is just does not exist. So this limit does not exist here, okay? One side is going up to positive infinity. The other side is going down to -infinity. Now, For this one, limit as x goes to 2. What's going on with 2? Let's do our little finger pointing here and see what happens. So I'm going to take it. I'm coming down, and hit to what looks like a little, like 1/2 on that side, right? But whenever I do my finger pointing over here and I'm coming down, this goes to -2. What happened? My two fingers, they didn't meet up, did they? Okay? If the two fingers don't meet up, what does that tell you? That tells you, by our common reasons why they don't exist, right here, number 2, or number 1, right? Number 1 common reason, okay, they don't meet up, because they approach different values on different sides. So the question becomes, is it a 1/2 on one side, or is it -2 on the other side? And so you can't just pick two different values for a limit, so the limit does not exist. It falls apart. There's this jump between these two values right here. You can clearly see that jump. So the limit does not exist. You think about it, your fingers don't line up when you run your fingers along the right side and the left side. They don't meet up. Okay, what about the limit at 5? Now we know if I just plug in 5 here, I get 1. Okay, how do I get 1? Well, 5, well, hold up. Does that even make sense? Because look, 5, we determine if I plug it in here, it doesn't work because it's too big. If I plug it in here, it's too small. So if I plug in 5, what happened? It just does not exist, right? But what do we know? As we approach the 5 on the left side, it's getting close to 1. That's what this is saying, right? As we approach the 5 on the right side, it's also getting close to 1, right? That green side is coming down, and that's getting close to 1. So it looks like our fingers meet up, except for at 5 itself is not defined. It's undefined at 5 itself, but it looks like it's defined for every value in the open interval near 5, right? So this idea, this limit is perfectly fine, and this is where calculus is powerful, right? It's really a pretty interesting idea that's going on here. In calculus, we care about everything around this point that's heading towards 5, but not actually what happens at x equal to 5 itself. It's really a backwards way of looking at everything. I kind of think of it kind of like you have a window, okay? If you've got a window, have you ever seen a window and it's got like the little dividers? You've got those little panels or whatever in your window. Well, this is how calculus is versus algebra. In algebra, it would be like we're pretending like we cannot see through anything but this skinny little piece right here. And all that we care about is the value x equal to 3 or x equal to 5 or whatever it is, right? Okay, that's all we care about is this little narrow blip right there. That's algebra. But in calculus, instead of looking at that little narrow blip, we say, okay, ignore this little narrow blip and let's look at the pretty view that we have outside the window, right? We care about what everything else looks like outside of this view here, right? So it's all these x values looking through here that we're actually looking at and we're concerned with in calculus. So just a little analogy that maybe helps, maybe it doesn't. All right, the limit as x goes to 6. So at 6, it looks like we're going to have ourselves a pretty big issue here. There's a vertical asymptote. That function, when we plug in 6, is undefined, so the limit does not exist. Now, when we get into infinite limits, we will talk more about this scenario here. But for now, we're going to say that the limit does not exist, okay? Baby steps, people. All right, guys. Well, that ends this part of the video. And I hope that this kind of helps you a little bit more with graphical interpretations of limits and using your fingers to look at both sides of the curve so that you can kind of narrow down your answers. All right.